Are there questions from last time? Okay, so if not, let me begin. So if you recall last time, what we tried to understand is how to calculate the correlation function of the disk, because that's what you'll be needing in the presence of boundary. And what we had said, first of all, that the overall normalization, okay, maybe I come back to normalization a little later. Okay. So if we have a correlation function of this kind, etc., then the B's and the C's, etc. Then one way to simplify this correlation function is to map it to a correlation function on the disk, okay, or on a sphere. So map this to correlation function on the sphere or the disk or the complex plane. Okay. And the rules, okay, are that we can replace B bar of X plus IY because it was in the say upper half plane to the complex plane. So we are working in upper half plane. This is in upper half plane. We replace B bar of X plus IY by B of X minus IY, C bar of X plus IY by C of X minus IY. Okay. And similarly, if we have del bar X mu of X plus IY, we replace by plus or minus del X mu of X plus X minus IY. Here plus will be for Neumann, minus will be for Dirichlet. And similarly for psi mu. And also e to the phi, etc. Okay. So the general idea is that if you have usual Neumann type boundary condition, then you have a plus sign, otherwise you have a minus sign, right? If you have Dirichlet boundary condition, then you have a minus sign. Okay. And similarly for Ramon and Neveu-Schwarz, things are different, right? So whatever boundary condition the psi satisfies, that fixes what the replacement rule should be, whether it should be plus or minus. Okay. So I'll illustrate this by example. Suppose we have product over I e to the I k parallel dot x of, let's say, xi plus I. So maybe I made a mistake here. I should have said something else. This, okay, e to the I k dot x I didn't explain. That also I should do. Okay. So before I start to the example, if we have e to the I k parallel dot x plus I k transverse dot x, at x plus iy. This has to be replaced on the plane by e to the I k parallel x plus I. So this is transverse I k transverse dot x of x plus iy times e to the I k parallel dot x minus I k transverse dot x at x minus iy. Where here k parallel is the momentum along Neumann direction, and k transverse is momentum Now recall that open strings do not carry momentum along the Dirichlet directions, right? But here we are talking about operators inserted in the bulk, which essentially come from closed string vertex operator. And the closed strings, of course, have no such restriction, right? Closed strings live in the full space time, so they can have momentum transverse to the brane as well as tangential to the brane. Okay? And the idea is that if you have something like this, then you have to replace it by a product where you have an insertion on the upper half plane as well as an insertion on the lower half plane. Okay. And the justification of these rules is essentially the method of images. Okay. So for free field, right, all the correlation functions are obtained by Green's functions, right? So for free fields, which is what we have, free fields, correlation function are obtained from Green's function. Okay. So what we need to do is we need Green's function on the upper half plane. With appropriate boundary condition on the real axis. And this can be done by using method of images. Okay. So, for example, okay, let's look at this replacement rule. That imagine that you are trying to calculate the Green's functions of the x's in the upper half plane, okay, in the presence of operators like this. Now, to calculate Green's function in the upper half plane, okay, we make use of the OP of x with these operators. Right? Those are the allowed singularities of the Green's function. Let's imagine that you have some del x at some arbitrary point z prime and del x at some z double prime. Okay, so you are trying to calculate the Green's function of these 2-point function in the presence of operators like this. So it has certain singularities around this. Now, when you put an operator in the lower half plane, okay, it makes no difference to the singularities because we are always restricted to the upper half plane. Okay. But it, of course, changes the Green's function in the full complex plane, right? We have additional singularities. Okay, so it will change the Green's function. Okay. And the point that one has to verify is that with this rule, okay, it's always ensured that if you have del x, if you calculate the correlation function of one del x and another del x, okay, then on the real axis, okay, del x will become equal to del x. Del x will become equal to del bar x for parallel momentum, and del x will become equal to minus del bar x for transverse directions. Okay. So it's essentially the method of images that leads to this rule, as well as all the other rules that you saw in the previous slide. Yeah.
What did you say in the second part that you this singularities and all? Could you repeat that?
Yeah. So what I said, let's suppose that we are trying to calculate, we want to make sure if this, say, let's say one insertion to the ik dot x plus iy, and you have del x of some z, del x mu1 of z, del x mu2 of z prime. Okay. So you are trying to calculate this two-point function. This is holomorphic. So this two-point function you can calculate using the OP between the singularity as a function of z. Suppose you are trying to look at it, you are looking at it as a function of z. We can calculate it knowing its singularities, because z has a singularity at z prime with certain residue, and z will have a singularity at this point with certain residue. Okay. And it has to have follow up sufficiently fast at infinity, that we know, because we are taking this is a dimension one operator. So using this, we can fix this completely on the upper half plane or on the full complex plane.
Yes.
But
Okay.
on the upper half plane, okay, there is some freedom. Okay. The upper half plane, because you are not demanding analyticity in the full complex plane. Okay. So in the upper half plane, just knowing the singularity doesn't fix the correlation function uniquely, but you need also the boundary condition on the real axis. So on upper half plane, we also need boundary condition on the real axis. Okay. Namely, the del x mu z should be equal to del bar x mu z plus or minus, where plus for Neumann and minus for Dirichlet. Okay. So this boundary condition is something you have to use in addition to the singularity structure.
Okay.
And the point is, if we now put a image charge, okay, some image in the lower half plane, it doesn't affect the singularity structure, but it of course changes the correlation function, because on the full complex plane, right, you also have additional singularities in the lower half plane. So it will change the correlation function. And what one can show is that the rule that I gave, namely that you have to replace it to the ik parallel dot x plus ik perp dot x by this product in the full complex plane, essentially guarantees that the boundary condition on the real axis is satisfied. Is this statement clear?
But how is that true for the other vertex operators like B and C? Because you are not putting it in just upper half plane, right? You are removing the upper half insertion and putting it in the lower half.
Exactly. So what happens is that if you have correlation function of the B's only, right?
Yes.
Okay. Then when you move a B bar in the lower half plane, so B has no singularity with B bar anyway. Okay.
Yeah.
So you remove B, or B has no singularity with B bar or C bar, right? So you are removing B bar and C bar and putting this in the lower half plane as B and C. Okay. So as far as B is concerned, there is no change in the singularity structure.
You mean these additional things will only lie in the lower half plane? Or
Exactly. Okay.
additional
The
singularity.
additional things will only lie in the lower half plane. So let me repeat again. So what we had said, that if we have, let's look at the BC. Product over B, product over C, product over B bar, product over C bar. This will be replaced by product over B, product over C. Okay, product. Product over, what happened here? And here it will be product over B at x minus iy, and product over C at x minus iy. Okay. So you replace the B bar and C bar by the corresponding B and C, but in the lower half plane. Okay. So now let's look at the singularity as a function of one of the B's. So that B has singularity with, when you take the product with C, and it has zeros when you take the product with B. Okay. Those remain intact because we are not moving B and C. Okay. B had no singularity near B bar or near C bar. So if we remove B bar and C bar, it doesn't affect the singularity of B. Okay. And the same thing is true for C. Okay. Now you can ask, what about singularity of B bar, right? You see there is a B bar here, right? So when B bar of the first say, let's take B bar of some x plus iy with C bar of x prime plus I y prime. These had a singularity of the form 1 over z minus z bar. So x minus iy minus x prime plus iy prime. Okay, because B bar of z, C bar of w has a 1 over z bar minus w bar. Okay, so that's what I have written here. But this is being replaced by B of x minus iy and C of x prime minus iy prime, which gives you 1 over x minus iy minus x prime plus iy prime. So it's exactly the same singularity. So if you replace B bar and C bar and replace and move them in the lower half plane, it has exactly the same singularity structure. So the singularity structure you are not affecting at all by moving these all the B bars and C bars to the lower half plane with argument being complex conjugated. The advantage of this is that now the boundary condition, if you had a B and a B bar, right? Imagine that you had a B and you try to replace the B by B bar and C by C bar. Okay, that will conserve ghost number. And now if you go near the real axis, you have to make sure that if you replace B by B bar and C by C bar, the result should follow the boundary condition that B is equal to B bar and C equal to C bar on the real axis. And this is guaranteed by placing these operators symmetrically.
Can you explain why this z minus? I mean, there's a difference between 1 by z minus z prime and 1 by z bar minus z bar prime, right?
Yes, exactly. Okay, I'll explain. So you remember what was the OP, right? B bar of, or B bar or B tilde, we had called it B tilde probably, right? It is B tilde of whatever argument, C tilde of Z prime went as 1 over Z bar minus Z bar prime. And B of Z, C of Z prime went as 1 over Z minus Z prime. Okay, where Z and Z prime represents where you have placed the operator. So in particular, if you take B tilde of x plus iy, the actual location, C tilde of x prime plus iy prime, this should go as 1 over z bar minus z bar prime, right? So z bar is what? X minus iy, right? And z bar prime is minus x prime plus iy prime, right? So B tilde of x plus iy, C tilde of x prime plus iy prime should be like this. What you are saying is that we are going to replace it by B of x minus iy and C of x prime minus iy prime. This are B and C, so it of course goes as 1 over z minus z prime, so which is what over 1 over x minus iy minus x prime plus iy prime. Is this clear?
Yes, yes.
Okay, any other confusion? Okay. The fact that we have B equal to B bar is something you have to check. Okay, so let me emphasize this point once more, right? Suppose you have a product which is product over I B of say xi plus iyi product over j c of x prime j plus iy prime j product over k v tilde w I plus I wk plus I uk and product over L. To call this B and then the B tilde of W prime L plus IU prime L. Okay. Imagine that you have this on the sphere, on the plane. This correlation function you are calculating on the plane. Okay. Now, the question you are asking is if we bring, say, B, suppose we take y1 equal to 0 and y prime 1 equal to 0. Okay. Then we have something like B of xi, C of x prime, so B of x1, C of x prime 1, and then the other things. This is not in general equal to B tilde of x1, C tilde of x1 prime times other things. Right? Because there is no reason why the B and B tilde, if you replace B and C by B tilde and C tilde on a general correlation function on a plane, the correlation function should be equal. On the other hand, if you are trying to calculate this correlation function on the upper half plane, then it should be equal, right? You can, if you replace B by B tilde and C by C tilde, it should be equal. Okay. And what I'm saying here is that by the replacement rule that I gave, which is that if you have B tilde, then you should replace it by B tilde in the lower half plane, or B in the lower half plane. Okay. Those rules automatically ensure that this is true. Right? Because now you see, instead of having to deal with B tilde and C tilde, this is C tilde. This is C. No, we did something wrong here. So this should have been, this is BC, so C tilde and B tilde. Okay. So the point is that in general, this is not true. But if we arrange the insertions by using this rule that I gave, okay, that the argument of B, that B bar will be replaced by B and C bar will be replaced by C with arguments complex conjugated. Okay. Then you can verify that for such correlation functions, this will always be true. Okay, essentially by construction. Is this clear? Okay. So one should keep in mind that the correlation functions on the plane are different from the correlation functions on the upper half plane. Okay. On the upper half plane, if we have B tilde and C tilde insertions, you just replace it by a BC insertion on the plane with complex conjugated arguments. Okay. So in some sense, the correlation functions for the upper half plane can be mapped to just correlation function in the holomorphic sector of the full complex plane. Okay. The only exception is for the e to the I k dot x terms, right? Because there is no, at least for the zero mode, there is no natural factorization between left and right. Okay. So there the replacement rule is what I said, e to the I k dot x, you have to replace by, you have to also put in e to the I k dot x in the lower half plane with k parallel remaining unchanged and k transverse changing sign. Is this clear? Okay, so let me give some examples. Okay, then imagine that we have some products like this, product over I to the I a parallel dot x of xi plus iyi, sorry, k parallel plus dot x plus in the upper half plane. There may be ghost insertions because otherwise, of course, the result will be 0. So this is supposed to be equal to product over I to the I ki parallel dot x plus in the full plane. Okay, that was the rule. And then the ghost insertions will be there. So this means now you look at in the full plane, okay, when you calculate correlation functions like this, of course, you have momentum conservation. Okay. So this will be proportional to a delta function of sum over ki parallel plus sum over I ki parallel. But you see, there is no momentum conservation. There is no the argument of the for the transverse momentum. Okay, it just gives you 0. Okay, so this is delta parallel, and they'll get a delta transverse of 0. Okay. So for the transverse direction, there is no associated momentum conservation. Okay. The momentum conservation comes, sorry, this is because there are these two factors, right? This and this. Okay. So the momentum conservation is only for the momentum that is parallel to the brain. Okay. And this, of course, agrees with the physical intuition that if you have a D brain, okay, then there is translation invariance along the brain. So you should have momentum conservation along the brain. Okay. But there should be no momentum conservation transverse to the brain because a closed string can come and hit the brain and get reflected. Okay. Essentially, the momentum is getting absorbed by the brain, but because the brain is infinite extent, right, that has no effect on the brain at the end. Is this clear?
So how do you interpret this delta 0?
This is basically the volume of the transverse space, right?
Infinite.
Yeah, delta function of the momentum, right, basically means that the transverse, I mean, delta of 0 basically means it's the infinite volume of the transverse space, right?
In principle, you can have D branes also compact, right?
Yeah, D plane is also compact. Then this will be quantized, right? Here it's the transverse direction. If the transverse direction is compact, then this will be replaced by the volume of the transverse direction.
Okay.
Any other question? Yeah. In fact, strictly speaking, right, if you do this computation appropriately, right, because x is actually localized, right? I mean, the 0 mode one has to treat a little more carefully here. Okay? So remember, where is the delta function coming from? Okay, this delta function, strictly speaking, this delta function is not really there because the delta function comes. Let me do that next. This delta of k basically comes from the integral e to the I kx dx. Right? This is a 0 mode integral. Okay? You remember that even for the point particle mechanics, we had described the origin of this delta function. It's the 0 mode integral that produces the delta function. Okay. Now for the D branes, what happens is that the brain is actually localized, right? The brain is localized at x equal to 0 or whatever. Okay. And so because of this, okay, the x integral in fact has a delta function, right? That's another way of saying this. So x integral has a delta function. So there is intrinsically delta x that is built in. So you get it to the I k dot x delta x dx, and this is just 1. Okay, no constant on k. Okay, that's another way of saying this. So here, I mean, if you don't use the fact that the D brane is localized at a given point in the transverse direction, then you get that delta of 0. Okay? But once you use the fact that the D brane boundary condition forces the center of mass to be at 0, then you really don't have the delta function.
This is only for the transverse direction.
Transverse direction, exactly.
Okay.
Okay. Any other question? Okay. So let's try to apply this. Okay. So first, let's look at the bosonic string. Suppose you are trying to calculate a one-point function of a vortex operator. Okay, the important ones are the massless ones. It could be graviton or dilaton. So we had seen that one-point function. So you have to calculate. So if suppose C bar V or C tilde V is the usual vortex operator. On the disk, we need to calculate half, okay, C bar V. Okay. This comes because of there is a conformal killing vector. So we are calculating this in the upper half plane. Okay. And the result, in fact, should depend on where you place it. Okay, this is a dimension 0 primary. Okay, and by making using an SL2R transformation, you can push it anywhere on the upper half plane. Okay, so it doesn't really matter where on the upper half plane you are doing this calculation. But let's suppose you want to do this, you want to put it at I. So location doesn't matter. Take it at I. You are calculating C, you have a half del C of I minus this is on the upper half plane. Now let's suppose that V is the graviton vortex operator. So del X mu of I del bar X mu of I. Okay, graviton or dilaton, and we are looking at the zero momentum. Okay, in fact, zero momentum doesn't matter because in this case, if the d brane, if the momentum there, if the momentum is transverse to the brane, it doesn't really matter. Okay, it's only the momentum tangential to the brane for which you have to put it equal to 0 because of this delta function. So this will be given by half del C of I minus del C of minus I, C of I, C of minus I, del x mu of I, del x mu of minus I. Okay, in the plane.
Sorry, Ashok, I'm slightly confused. You wanted to put the vertex operator on the origin on the disk, right?
Yes.
And that
The
corresponds to
but as
iota
I
and
said,
the
it doesn't really matter where you put it, right? Because the disk also has SL2R, right?
yeah.
And using that SL2R, you can move the vertex operator anywhere.
Yeah, and on top of that, you can also choose the position for this del C minus del bar C, C bar.
No, it's at the same place. This
So
is this whole thing is the vertex operator.
if you had 2-point function on the disk, you will attach 2 of these del C minus del bar C bar.
No, no. For 2-point function, there's no confusion, right? Because 2-point
Yeah.
function on the disk doesn't have a CKV.
Okay.
Okay. So then you will put CC bar V and C2 CC bar V, and then you have to use the you have to insert one B according to the transition function.
Okay.
Okay. So for 2-point, so this is very specific to 1-point function on the disk, because when you have disk with one puncture, that has a conformal killing vector. Okay. Normally, you wouldn't deal with such things because conformal killing vector makes things vanish because you are dividing by the volume. Except that in this case, the group is compact. Okay. And so we can make sense of it. And the statement that I made last time without proving it is that the rule is that you have to replace the CC bar V by del C minus del bar C bar multiplied by CC bar V. Right? So this will be the new vertex operator. So this operator you can put anywhere on the upper half plane. The result is independent. Is that statement clear?
Yeah.
Okay. So that's why I'm putting everything at I. Okay. I could have put it at x plus iy. Okay. As I said, you can easily check that the results will be independent. Okay. So this can be easily calculated, right? Because so what we have, let me divide it into some parts. So del C of I, C of I, C of minus I, minus del C of minus I, C of I, C of minus I, and del x mu of I, del x mu of minus I. Okay, these in fact so this 2-point function basically gives you minus eta mu nu over 2 times I minus minus I square. Okay, this is from the del x OP. Remember, it was minus eta mu nu over 2z minus w square, and that's what I'm using here. Okay. These ones you can calculate. So the C correlation function can be computed from C of Z1, C of Z2, C of Z3 is equal to K okay. K is unknown at this stage. Okay, we'll see later how to determine K. Okay. And I said that we cannot normalize it to 1 because for the closed string, right, when you had C, 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 C tilde, C tilde, C tilde, then we can choose the normalization to be anything that we like by adjusting the normalization of C and compensating the corresponding normalization of B so that the BCOP remains unchanged. But once you have done it for closed strings, you have no choice on this constant, right? So you have to keep it as a free parameter for now and determine it by consistency at the end. Is this clear? Okay. So using this, you can easily determine this correlation function. Okay. So we'll get using this del C of I, C of I, C of minus I. Basically, it will give you 2I square times K. Okay, because this OP in fact has a Z minus W whole square kind of OP. And similarly for the other one. And you can easily check that if instead of I you had taken something else, right, then this will change, but this will also change. Because instead of I you will have something else and they will just compensate, right? You will get a 1 over Z minus W square from here and Z minus W square from the C, and they will just cancel. Is this clear? So the point is that since we do not know K, we cannot determine the overall normalization of the 1-point function. However, we can determine the relative normalization. For example, the ratio of graviton coupling to dilaton coupling. So using this, one finds that the coupling of massless fields to a DP brane okay, so this has to be qualified. So phi is the dilaton and G is the metric. Phi is the dilaton. But it is a dilaton on the brane. And G is the induced string metric on the brane. Induced metric on the brane. Okay, so if the brain, for example, is along the where you have set some of the coordinates to 0, okay, then this is basically G parallel. Okay, you have to look at the components of the metric along the parallel direction, and that's what will appear in this expression over here.
How will the ratio of the 1-point functions fix this?
Because if you now look at, so this is some unknown constant k or k prime, right? K prime is related to k. Because if you expand it to in the powers of phi and h, suppose you write g mu nu equal to eta mu nu plus h mu nu, right? Okay. Then you expand this in power series in phi and h. So this expansion will give you 1 minus phi times 1 plus h mu mu. Let me put it 2. So the half goes away, 1 plus h mu mu. So this is nearly equal to 1 minus phi plus h mu mu, right? Okay. So if you know the coupling of the dilaton and the coupling of the graviton, okay, so what is determined by the ratio of the 1-point function is the relative coefficient between these two. Okay. And then the structure you can get determined from the general coordinate invariance and some general property of phi, that when you shift phi by a constant, then the effective action essentially scales by a constant, right? So once you have this coefficient, right, you can determine this. So basically you are guaranteed I mean, from general structure, one knows that it's of the form e to the alpha phi times square root of determinant g, right? Because that's the general coordinate invariant form. And then this alpha you can determine from this analysis. Is this clear? Okay, so let me say it again, maybe. That's so the ratio of 1-point function gives you the ratio of terms linear in phi and h mu nu in the effective action. And then we use general properties like general coordinate invariance, general coordinate invariance follows from the fact that the pure gauge modes decouple, right? In all S matrix, the pure gauge modes decouple, and that implies that the effective action must be general coordinate invariant. Okay. So you basically use general coordinate properties like general coordinate invariance to determine the form of the effective action. Is this clear? Okay. So this is, so maybe I should have said the how is phi normalized. Okay. So this normalization of phi, so you have to first look at the closed string effective action, right? Just from the closed string amplitude, from closed string amplitude, we know that massless scattering amplitude at low energy is captured by the effective action, okay, which has this form. So S closed integral d 26 x e to the power minus 2 pi, okay, square root of determinant g, and then the Ricci scalar, and then I think there is a minus grad phi minus alpha sigma h mu alpha h rho tau sigma. Okay, so this you know from the analysis of the low energy scattering amplitude in the closed string theory. Okay, so that fixes the normalization of the vortex operator, right? I mean, this of course is true. Only I think there is a minus 4 here. This is true only if you have normalized phi in a certain way, right? And normalize the metric vortex operators in a certain way. So you fix the normalization of the vortex operators just by comparing with this effective action. And after that, there is no further ambiguity in calculating the ratio of the 1-point function for the on the d-branes, right? Because the same vortex operator you will now use for this calculation over here, this v.
Is there no consistent way to reduce that action to on the world volume theory of a brane?
Reduce this action?
Yeah, at the level of action, like forget about disk 1-point function, but
yeah, because this action doesn't know anything about the brane, right?
yeah, but can you supply the details of the brane without going back to world sheet?
Not really, no. Because the properties of the brane, right, you have to go back to the worksheet. Because otherwise, how do you know what kind of brane you have, right?
Yeah, I don't know.
Yeah, so the fact that it's a D brane, right? So this coefficient is crucial in the fact that it's a D brane. Okay, for another brane, this could be, see, this square root of determinant G structure you could have guessed, right? Because that's just from the covariance. But what will multiply it, right? That's a property of the brane.
I see. Yeah.
So what this is saying is that if you expand this out, right? So this is, of course, I have said from the 1-point function, okay? But this effective action, when I've written the effective action like this means that if you expand this out in power series in phi and h mu nu, okay, then this will describe the low energy scattering of arbitrary number of gravitons and dilatons in the presence of the d brane. Is this clear? Are there questions?
Yeah, I have a question. So, I mean, about this, whether we can write an effective action for the brain. I mean, if I consider the amplitudes and the disk corrections to the amplitudes, is the
Yes.
statement that I don't have a consistent way of writing the effective action?
No, you
Or,
can. That's what you are saying, writing here, right?
but that's just the disk. This doesn't know about the closed string.
No, phi
Or,
and g are closed strings, right?
okay.
See, because this is not an effective action for open strings. You can also include the open strings, right? Which I have not done.
Oh, okay.
Because there are gauge fields, right? So there will
Yeah.
also be additional terms that couple open string to the closed strings, right? Those I have not written. Okay? So this effective action is just, suppose you have a brane and you calculate scattering of closed strings, external closed strings in the presence of the brane. Right? This
Okay.
is the effective action that tells you how much the scattering amplitude will differ from the scattering amplitude in the absence of the brane. right? Because this effective action already gives you some scattering amplitude, right? That's in the absence of the. This will tell you the extra effect because of the brane.
Okay.
And from the world sheet perspective, this is capturing the effect of the disk, right? That when you calculate, say, n graviton and m dilaton amplitude, you have the usual sphere contribution, but you also have a disk contribution. This effective action captures the disk contribution.
Ashok,
But it also captures the sphere as well, right?
No, the sphere is captured by this. So the
Okay.
total effective action is this, which describes scattering in the bulk. Okay? And on top of that, you have this, which describes the scattering from the disk, from the brane. Okay? So let me try to describe it pictorially, what is happening here. Okay? Let's imagine that there is a brane here, right? Which falls, suppose is a p brane. We have closed strings here. So you can, of course, have scattering far away from the brane, right? Which knows nothing about the brane. Those scatterings will also have to be captured by something, right? That's captured by the bulk action. So scattering away from the brane is captured by the bulk action. Captured by bulk effective action. An extra contribution due to the brane is captured by the additional term.
So I should just picturize the complete action as sum of the two.
Yeah,
or-
exactly. You should
Okay.
picturize the complete action as the sum of the two, right? But one should keep in mind that while the bulk action has integration over all 26-dimensional space-time, this one has integration only over the p plus 1-dimensional space-time, because this is localized on the brane. Yeah, but the full action is the sum of the two.
Ashok, can you clarify this thing that you are trying to say that both phi and h have a 1-point function on the brane?
Yes.
But don't we say that when non-scalar fields get a expectation value, vacuum expectation value in QFT, we have Lorentz invariance is broken and all?
No, it's only the trace of H which is getting vacuum expectation value, right?
Trace of h. That is fine.
Lorentz invariant.
Yeah.
Okay. Maybe I should say it's trace of H, but it's trace of H in the parallel direction. So Lorentz invariance is broken because the brane breaks Lorentz invariance, right? So this is H parallel mu. H parallel. There's a transverse. There's a contribution from the transverse direction.
But Lorentz invariance is only in the parallel direction.
Exactly. So that is preserved.
That is preserved, yes. Because you're only giving expectation value to trace.
Exactly.
Yeah.
Okay, and you can see from this also, right? This doesn't break any Lorentz invariance in the parallel direction, right? Because it has general coordinate invariant form.
So Ashok, the full picture now would be like we have this bulk effective action that comes from only the sphere and all those kind of diagrams, and
Yes.
then this contribution that comes from some Riemann surface with boundary, and those are like with background some brane.
Exactly. Right. So the interpretation of these is that these are giving additional contribution to the effective action due to the presence of the brane.
Mhm. And how can we see that if we are not close to the brain, then the effect should be lower? How can we see
Because
it
this,
from
yeah,
here?
because this integral,
Uh-huh.
right, is localized on the brane, right?
Oh, yeah, yeah, yeah. We are
So,
doing integral.
so when I write x, right, it is
Mhm.
x parallel and x transverse equal to 0.
True.
And
Okay.
similarly here, it's x parallel, x transverse equal to 0.
So if we are like close to the brain, then it can happen that the amplitude gets more contribution from this rather than the bulk contributions.
That's right. Yeah, that can certainly happen.
Mhm.
Any other question?
It will still be GS suppressed, right? I mean,
Yeah, it's still
No.
GS suppressed. In fact, since you brought up the question of GS, like we can also see from here, okay, that that is another way of seeing this e to the minus phi. That here, right? I mean, we have said that the coupling constant is set by the dilaton, right? So e to the minus 2 phi, right? The expectation value is like 1 over GS square. And this is also consistent with the fact that e to the minus 2 phi multiplies the whole action, because that means that when we expand around the vacuum, there's a 1 over GS square multiplying the whole action. So from that perspective, we can see that e to the minus phi is like 1 over GS. Okay. So this basically tells us that the de-Broglie tension goes as 1 over GS. Okay. Now we'll see later explicitly how to actually calculate the de-Broglie tension. Basically, for that you have to calculate K prime, right? So what I'm saying implicitly here is that the K prime is GS independent. The GS dependence comes because e to the minus phi was 1 over GS. Okay, but we will see later how to calculate the tension explicitly. Any other question?
so this K prime is the sort of relative coefficient between the bulk action and this bulk effective action and the
And the
boundary
boundary
effective action.
action, exactly. That's right.
Okay, and it's the same K prime like we were discussing around the CCC.
Exactly. Yeah. Because this K prime is related to the fact that the open string that on the disk, right, the normalization of the correlation functions is ambiguous, right? And that ambiguity is what is appearing in this K prime. Okay. So in superstring, it's more or less straightforward. So there, the graviton vortex operator or the massless vortex operator is of the form C tilde e to the minus phi psi mu e to the minus phi tilde psi tilde. Right? This is in the NS sector. This is NSNS. So then again, the 1-point function. This is called upper plane. Let me HP. And this will now be replaced by del C of I, C of I, C of minus I, minus del C of minus I, C of I, C of minus I, times e to the minus phi I, psi mu of I, e to the minus phi of minus I, psi mu of minus I. And again, we can calculate this, right? Because you see that you have the correct picture changing operator, e to the minus phi, e to the minus phi gives you e to the minus 2 phi, psi OP, you know, right? 1 over z minus w. And again, this, you know, right? So this is again given by k times something known. And k is the normalization. So using this, we can determine the ratio of graviton to dilaton one-point function. And that essentially again leads to the following same kind of action, e to the minus phi square root of determinant G parallel dp plus 1x. Okay, so even for bosonic, for superstrings, right, the d brane, the effective action on the d brane for NS fields takes this form for NS fields. The difference comes in the Raman fields. Okay, so what about RR fields? So first of all, on the disk, for disk one-point function, disk one-point function, we are forced to work with minus 3/2 minus half picture, or the other way, or because the total picture number will have to add up to -2, and if you start with minus half, then the total picture number is -1, and the picture changing operators only increase the picture number, so you cannot get to -2. So you are forced to work in these picture numbers, and that is in a sense good, because this is telling us that now the coupling can be to, there can be coupling to the gauge fields. There can be coupling to gauge fields instead of field strength.
Why couldn't you have worked in -3 of -3 of?
No, you can. Then you have to put an extra PCO.
Yeah.
Right? It will just make life a little more complicated.
Okay.
Right? But -3 of -half and -3/2 are good enough. So if you recall, we had argued that in the -half picture, the vertex operators couple directly to field strengths. Okay, because there is no gauge invariance in that sector. Okay, there is nothing which is called pure gauge. Okay, which basically tells us that it must be directly coupling to the field strength, because field strength is gauge invariant. On the other hand, -3 of -half and -3 of picture allows for gauge transformations. So here, the vertex operators are actually coupled to the gauge fields rather than field strengths. And on-shell vertex operators had a form. So on-shell vertex operator had the form C tilde e to the minus phi by 2 This is for 2B and S tilde B for 2A. So important point, which I had, I think, mentioned earlier also, that in the minus of picture, 2B has the property that the chiralities of the spinors are the same in the left and right sector. In 2A, they are opposite. But with the same rule, now you see in what we have done here is that we have replaced e to the minus phi tilde by 2 by e to the minus 3 phi tilde by 2. So the GSO property of this is opposite of the GSO property of e to the minus phi tilde by 2. Okay? Because you have put in extra e to the minus phi tilde, which is GSO odd. Okay? This means that in order to have a valid GSO even vertex operator, we must change the rules. We must change this also, the chirality of this. Instead of S tilde A, we have to use S tilde A dot. And it's the opposite for 2A. In 2A, in minus of picture, they had opposite chirality. In the minus of minus 3 of picture, they'll have the same chirality. Okay, I think this is minus 3 half minus half, right? Because in the left sector, you have taken to be minus 3 half, in the right sector, you have taken to be minus half. Is this clear? So what we need to do is we need to calculate. Let me contract it by some polarization, which I'll call zeta AB dot. So this is in 2B. Okay, 2A will be opposite. Now you want to make the replacement. But to make the replacement, we know how to replace C tilde, we know how to replace it to the minus 3 phi tilde by 2, because phi tilde will be replaced by phi with an opposite sign here. But what about this one? So for this, we need to recall that S tilde V dot of I was given by gamma 1 to gamma 9 minus P. These are the transverse directions. Not I, this is equal to on the boundary. Yes. You remember this? This is what we had determined last time, right? What kind of boundary condition is there on the spin fields? Okay. And for type 2B, okay, where P has to be odd, right? That's what we had found, because we have to replace S tilde B dot and S C dot. Okay, so in type 2B, we have a boundary condition that S tilde B dot is given by this. Is this clear? The fact that these two are the same is related to the fact that P is odd.
Sorry, in type 2B, there are only one chirality, right? Or is it that type 2A?
Yeah, there is one chirality, but as I said, once you go to the -3 picture, the chirality gets changed, right?
Okay.
So
Okay.
that's why you have to keep, you making use of both chiralities, right? At the end, of course, when the construct the vertex operator, there's only one chirality which will be left. Right?
But you have already written the vertex operator.
I have written the vertex operator, but now I'm writing the boundary condition on the spin field.
Yes.
Right?
No, one chirality will be left in what? In the
That
what
at
volume
the end,
theory?
you will get the correct combination of the chiral vertex operator. Right? Here, for example, let's look at this. Right?
Yeah.
This is a type 2 vertex operator, right?
Yes.
Okay. So in type 2b, then S tilde B dot. Okay. We have to find out what S tilde, what boundary condition is there on S tilde B dot.
Okay.
And we are saying that this is a boundary condition that we have on in type 2b.
So in the upper half
The
length,
boundary condition on P branes.
this is on the real line basically going to impose.
On the real line, exactly.
Yeah.
On the real line. Okay. So if P is odd, so for odd P, this makes sense. For even P, we will have S tilde B dot as gamma 1 to gamma 9 minus P B dot C SC. Okay, because for even P, okay, the chirality will change, right? Because for even P, this product has an odd number of gammas, and that will change the chirality. And this is a relevant one for 2A. Is this clear?
The SB dot there in the correlator, it's coming because we are working in -3/2.
Yes, exactly.
Otherwise, in 2b, it's always SB, right?
Yes, exactly.
Okay, okay. And here you're saying now we didn't study for 2b what to do if there is S tilde, SB dot.
Exactly. But just from Lorentz equation, same kind of argument, we can see that this has to be
Right,
like,
right. Okay, okay.
okay, that's all I'm saying.
Okay.
Is this clear? Okay. So then the replacement rule, okay, will be that this one, S tilde B dot of I, this should become, so this should become gamma 1 to gamma 9 minus P B dot C dot S C dot of minus I. Okay, it's basically the same kind of logic. That this will become this times SC dot of minus I. And so now we have again reduced the problem to calculate the correlation function on the plane with this kind of vertex operators. Is this clear? Are there questions? So then the correlation 1-point function. So 1-point function of RR fields on the disk. So that becomes del C of I minus del C of minus I, C of I, C of minus I, e to the minus 5/2 of I, e to the minus 3 5/2 of minus I, and then SA of I, and gamma 1 to gamma, sorry, SA dot I, something is not quite correct here, I think. Yeah, SA of I. Yeah, that's SA of I. Is this clear? Okay, we just replaced the S tilde B dot by this combination. So now you see that
Earlier we had like P odd for 2B.
earlier we had P odd for 2B. Sorry, this is gamma 1 to gamma 9
and
minus
9 minus P. Yeah.
yeah,
That
9 minus
but earlier we had P odd for 2B, right?
yeah, here now also
Or
you have P odd for 2B.
okay. So it's based on that you are using that intuition as well, that P
Exactly.
has to
Yeah,
be odd for okay.
exactly. Okay. Meaning otherwise you will see that there is no one point function. I mean, you can try P not odd, okay, but then at the end you will run into the fact that there will be no possible boundary condition. See, the point is that here this one e to the minus 3 phi by 2 minus I e to the SC dot of minus I, right? This combination is a well-defined operator in 2B, right? Because you have changed the A to A dot, but you have also changed from e to the minus 5 by 2 to e to the minus 3 phi by 2, right? So this is a well-defined operator in 2B. That's why it makes sense. If it was, if this was SC, for example, okay, then this would not be a well-defined operator in 2B.
Okay.
Okay. So the rule is such that if you start from a correct operator in 2B, okay, then even after you replace it by its image, it will map to the correct operator.
It's now I probably understand. It's like probably we want to preserve the gamma 11, whatever that gamma 11 chirality.
Exactly. Gamma 11 chirality, but gamma 11 chirality also include, I mean, that projection also changes depending on whether its number is 1 or 3.
Yeah. So it changes, so it has to compensate here.
Exactly.
So it's actually the GSO projection only.
It is GSO
Yes,
projection. Exactly.
yeah.
Right? Because GSO projection of e to the minus 5 has an extra minus sign, right? So e to the minus 5 by 2 and e to the minus 3 by 2 have opposite GSO parity. And that's the reason why this has changed to SC dot rather than SC.
Yeah.
Okay. On the left, on the right, you have e to the minus 5 by 2 times SA. Right? On the left, you have e to the minus 3 5 by 2 times SC dot. Right? And that together you are replacing it by its image. Okay? And that still has the correct GSO parity.
Yeah.
Sorry, was there a question?
No, it makes sense.
Okay, I can hear some voice, but I may be not related. Okay, so this then you have to calculate, right? So here the C ghost correlation function is okay. C correlation function is fine. Okay, phi is okay, right? That altogether you have to the minus 2 phi. So this correlation function is you can calculate. So phi is okay. Correct conservation law. Now let's look at what about this. Right? So you see that here we need, and there is a zeta A B dot, right? Which you should have. So here we need SA of I SC dot of minus I. Okay. Is this 0 or non-zero? So that's the question. On the plane. Okay. So for this, let's remember how you had represented SA. Right? It was plus minus I phi by 2, phi 1 by 2. So maybe Let me write it slightly differently. To the I by 2 plus minus phi 1 plus minus phi 2 to plus minus phi 5. Okay. Where even number of minus signs correspond to A, and odd number of minus signs corresponds to B. Now let's pick an element of A. Okay, let's take e to the I by 2, phi 1 plus phi 2 minus phi 3 minus phi 4 plus phi 5. Okay. So with what will it have non-zero two-point function? So this has non-zero two-point function. With the only thing that it can have a non-zero two-point function. So this is in A, right? This is of type A. We will have e to the I by 2 times minus phi 1 minus phi 2 plus phi 3 plus phi 4 minus phi 5. And you see that this is in B. This is type B. Type B dot. Right? Because now it has even number, odd number of minus signs. Okay. And this is true generally. So what this is saying is that the two-point function like this, in fact, is non-zero only when if one is of type A, the other one has to be of type A dot. Right? They have to have opposite chirality. Only then you can have a non-zero correlation function, non-zero two-point function. Is this clear? Okay. So this is non-zero. Okay. So let's call this some, define this some, say epsilon AC dot, right? Some tensor. Given an A, there is always a C dot for which this is non-zero. Just change the sign of all of the phi's. Okay. In contrast, SC is equal to 0. And similarly, SA dot SC dot is also 0. So going back here, we see that now we have a non-zero correlation function. So this then we can write, so this I can write as proportional to gamma 1 to gamma 9 minus P B dot C dot zeta, what do I write? Epsilon AC dot, right there. Epsilon AC dot zeta A dot B dot. Sorry, zeta AB dot. So this is saying that now we can in fact have a non-zero one-point function for the RR fields. Is that point clear? Because we started by calculating the one-point function of RR fields. Okay. And we are seeing that as long as P is odd, okay, which is true for type 2 B theory, all the indices match up correctly so as to produce a non-zero one-point function. Because epsilon, this two-point function pairs A and C dot index, right? And that's exactly what we have here, right? So that can be a non-zero component here and which will eventually produce a non-zero result for the two-point function. Okay. Of course, it will depend on what zeta you have chosen, right? If you choose the wrong zeta, then it can still vanish. Okay. But there is some choice of zeta for which this is non-zero. Are there questions? So the net upshot of this is that in the effective action, now we can, right? So the effective action in the presence of the brain. As the form from K prime integral dp plus 1 x to the minus phi square root of determinant G parallel plus integral C both of these integrals are along the plane. They are integral along the plane. Here you have a p plus 1 dimensional wall volume of the brain, right? A p brain has also the zero direction, right? And so this is the natural polarized vector, the natural tensor that can be integrated along the p plus 1 dimensional wall volume. Okay? And so this basically is showing that while the deep p brain carries both, has couples to both dilaton and graviton, but it also couples to the Raman p plus 1 form field. Okay, it provides the source for the Raman p plus 1 form. Okay. We also see from here, okay, because the ratios, as I said, can be computed unambiguously. Okay. So this is also saying that the charge, Raman charge that it carries, okay, is proportional to the tension that it has, the energy per unit volume. Because this coupling to the metric gives information about how much energy per unit volume it has. Okay, that is contained in this K prime. And from this, we see that the Raman charge is also proportional to the same constant K prime, because K prime basically comes from the normalization of the 3-point function, normalization of the disk amplitude, and that's determined once and for all. Right? Everything else is determined from OP. So next time we'll discuss how to calculate this K prime.
One question. So, I mean, can I say that this term is somewhat capturing something about the topology of this brain world volume? Because it's independent of
It
metric.
did not see, even if it has trivial topology, right? Imagine that brain wall volume is like a sphere, right? Even then, there will be an integral of the C on the sphere. It will not carry an innate charge, but because the integration from here may get cancelled by integration from here and so on. But this is still a local coupling that exists.
Okay.
On the spherical topology, right? Of course, it has a non-trivial. If it has a non-trivial topology, then it will be a non-trivial coupling, and then it will actually carry some charge.
Okay.
Okay? But this is just telling you the information that locally it carries charge, the charge density, right? That this part, right, even if you have a spherical brain, right, which has no overall charge, if we just identify this piece of it, right, that near this, it will produce, it acts as a source of the Raman p plus 1 form field, and it will produce a Raman p plus 1 form field in the vicinity of this.
Right.
Any other question?
If we go back to the correlator,
Yes.
like in when we don't have the boundary, when we work in 1 by 2 picture,
Yes.
there we will have two SA, like SASB insertion, right?
That's true. Yes.
So that will be 0.
That will be 0. Yes. And it will be 0 also for the other reason that you have e to the minus 5 by 2, e to the minus 5 by 2.
Okay.
Right. That will also be 0. Right. But that is not the correct prescription, right? The correct prescription is that you have to choose the vertex operation or total picture number adds up to -2.
No, not on the disk. Like if I just think of plane,
Oh, if you think of plane, yes.
then probably we need another insertion. I think we like.
Yeah. If on the plane, so on the plane, certainly if you take just one Raman vertex operator, right? Well, even one Raman, this doesn't necessarily. Yeah, if you have on the plane, SA and S tilde are independent, right?
Okay. Okay.
So the correlation function of if you have just one single Ramon insertion, the correlation function will vanish anyway, right?
Okay. Okay.
Because SA will not be able to contract with anything.
And about these like vertex operator that you have written here, so this is the statement that this is the only one which will have a non-zero OP with that.
Which is the only one?
The one you have written. If you
Yeah,
chose
exactly.
one,
You can see from here, right? Because if all of them are plus, then the only one with which it will have a contraction is when all of them are minus. Right? So in this basis, the correlation function basically becomes simple because each one is paired with a unique one.
right, right,
But
right.
this, of course, is a basis dependent state. Right? You can change your basis so that this changes.
Right, right. That's right.
But in this basis, it is true that each A is paired with a unique C dot, right? Which corresponds changing the sign of all the phi's in the exponent.
Okay.
Any other question?
But still one thing, like if say I change four signs but not the one sign, can it still can happen, right? That that OP will give me something regular, but other will give me something singular.
Yeah, meaning if you have also other vertex operators, then you
No,
can
no,
have
like
zero correlation function.
there are these five, right? 5 1, 5 2, 5 3, 5 4, 5 5, and I suppose in constructing this other one, yeah, that's my question. Like you changed sign of each of them.
Yeah.
If you don't change sign of say one of them,
Then the by phi charge conservation, it will give you 0.
oh,
Right? Unless you have another psi mu inserted somewhere else, which can carry, which can compensate for the phi charge. Because the field, the fermion fields are like e to the plus minus I phi, right?
yeah.
So those could compensate, but for the disk compound function, you don't have any other psi mu anywhere, right?
Okay.
So for this compound function calculation, the only pairing is this. And this essentially translates to the fact that only the Ramon P plus 1 form has a non-zero expectation value. Okay? Others have zero expectation value, right? That's of course consistent with Lorentz invariance, right? You could have said that even by from Lorentz invariance, but it's just a restatement of this fact over here.
Okay.
That this two-point function is given by a very specific tensor, right? Which I have called here epsilon AC dot. And once you put the tensor in, right, you find that the coupling is only of this form. Because this, in fact, is keeping track of the Lorentz invariance. Right? The fact that this two-point function is giving me as epsilon AC dot, right, is keeping track of the Lorentz invariance of the problem. Okay, it is basically saying that if you take two spinors of SO9, 1, right, then their product has an identity only if the two spinors are of opposite chirality. Right? That's a consequence of Lorentz invariance, right? SO9, 1 representation theory tells us that the product of two spinors can give a identity representation, the singlet representation, only if the two spinors are opposite chirality. Right? And that's what we are saying from this bosonized formula over here.
Okay.
Any other question?
So for the case of D in 2B, we have D9 branes. So the Ramon P form that will couple to it will be the dual of the zero form.
Yeah, it's basically a 10 form.
With the 10 form.
10 form potential. It's not a dynamical field, right? But nevertheless, I mean, there is a Ramon 10 form potential which can couple. Right? And that will make things inconsistent unless it's cancelled by something else. See, the point is, if the P brane is localized, right? I mean, that for a localized P brane, charge not equal to 0 is not problematic. Okay. Like for example, in 3+1 dimension, we can have point charge, right? This charge is localized, so it just acts as a source, right? And that sort of happen typically for localized p-brane. But if the p-brane is space filling, then of course the flux has nowhere to go, right? I mean, if you have a point particle in 3 dimensions, then the charge, then the flux just goes to infinity. Imagine in 3 dimensions you have charge distribution that is everywhere, right? Non-zero charge distribution. Then that's not a consistent background, okay? Because that produces a 1-point function of A0, which you can cancel against anything. So the same problem appears that if you have D9 brane, so for D9 brane, it's space filling. We have space filling brane. And this carries charge, carries 10 form charge, and is inconsistent. Unless the charge is cancelled. Cancelled by something else. And this is what happens in type 1 theory. Type 1 has a background charge. Which is equivalent to, say, 32 D9 branes with opposite sign. Okay. So in type 1 theory, what you do is that you cancel that background charge by putting precisely 32 D9 branes. And that's what gives rise to this SO32 gauge theory, gauge group. Okay, the reason that it's SO32 and not U32, as would happen for a D9 brane, is because there is also a projection in type 1, okay, that makes the U32 into SO32. Is this okay?
Yeah.
Any other question? Okay, so if not, I'll stop here and then I'll continue next time.